Welcome to EPG Pathshala lecture series on data analytics. In this particular module, we will be discussing about principal component analysis. Principal component analysis is actually a technique which is used for reducing the number of dimensions that may be used for analyzing our data. In this module, we will be learning about how to compute the principal components for a given data set, and we will also understand where this principal component may be applied. In other words, the applications of principal component analysis in analytics. To start with, suppose you are given with a very large data set in which you have multiple variables, that is more number of variables for the purpose of analyzing a data. And when you are trying to identify the correlations between these variables, you will be generating large pairs of correlations. And using these large pairs of correlation for understanding the data may be a difficult task, as well as it will be very complex from the audience perspective to understand the features available in the data. The second thing is, when you are trying to display the same data graphically, the graphical display may not be of very much useful. The reason is the data set has multiple dimensions. Therefore, you will have to identify a suitable way by which you can map the same data, but on a reduced set of dimensions. This is where principal component analysis comes into picture. So, when you want to interpret the data in a more meaningful form, then you will have to reduce the number of variables which is available in the data, and using those reduced variables, that is few variables, you can interpret the linear combinations that is available in the given data. Each linear combination will correspond to a principal component. So, the objective here is, given a data set, you need to reduce the number of variables available in the data set with which you can meaningfully visualize the data or interpret the data. Now, let us understand what is principal component analysis. This can be understood when we can visualize this PCA mathematically. Mathematically speaking, given a data set, we can represent that as n data vectors. This n data vector, assume it comprises of k dimensions. Now, principal component analysis will try to find C number of orthogonal vectors, where C is a number that is very less when compared with the k, which is the original number of dimensions available in your data set. And this C number of dimensions will be considered as the best dimension for representing the data. In other words, the original data set is reduced to comprise of less number of dimensions, say C number of dimensions from n dimensions, for the purpose of analyzing our data. Here, each dimension or each data vector will now become a linear combination of the principal components, where the number of principal components will be C as mentioned before. This principal component analysis works only for numerical data. That means, it will not work for text data is not true. Given any form of data, if you can represent that in numerical values, then this principal component analysis may be applied on any kind of data. But mathematically speaking, it requires numbers. When this principal component analysis is applied on number of dimensions, where the number of dimensions is too large, then the need for principal component analysis can be understood, or the significance behind the principal component analysis may be understood. Now, let us take a look at this diagram. Assume the data set consists of two dimensions, x and x1 and x2. The distribution of the data is given by this ellipse. So, with the two original dimensions x1 and x2, what we are trying to analyze it, whether the distribution or the variance of the data, whether it is large along the x axis, that is x1 axis, or along the x2 axis. Now, the principal component analysis will result in two other dimensions which are generated from the original two dimension x1 and x2. The two new dimensions that are generated, assume it is represented as y1 and y2. Now, with these two dimensions, if you can visualize the data, you may find there is wide variation along the y1 axis when compared with y2 axis. So, the original form of data which was showing variation more along both the axes x1 and x2, now when transformed to a new dimension y1 and y2, you may feel that more variation is along the y1 rather than y2. Therefore, you can start making use of the dimension y1 for the purpose of analyzing the data, and hence you may get effective results or interpretations about the data. PCA in general, when you represent mathematically, how it may look like. Consider there are n number of variables represented by x1 till xn, and now if you are going to represent the same n variables by means of new variables, say y1 till yn, then with the help of the new variables y1 till yn, you can make use of the original variables x1 till xn for representing the new variables. Here the y1 till yk are nothing but the principal components that are derived from the original dimensions x1 till xk. The y1, y2, yk are all orthogonal vectors. Since you are trying to work on a principal component, these principal components will be orthogonal to each other, that is, they will not be correlated with each other. Y1 here indicates an orthogonal vector which is showing high variance in terms of the data. So, you can find large amount of variance in the data along the y dimension. Then y2 will be the next axis or next dimension, transformed dimension, along with you may find larger variation in the data. So, when you order these principal components, y1 will be showing the high variance, y2 will be the next high variance, and yk will have the least variance highlighting the data. Now, when you are trying to make use of the new transformed axis y1 till yk, the y1 till yk has certain values like a11, a12, a1k, which are nothing but the first eigen coefficients. When you are representing the value y1, I told it is made up of the first eigenvector. So, the values a1, a12, a1k indicates the covariance or the coefficients which is collected from the original correlation matrix. Similarly, the second value a1, a21, a22, a2k indicates the second eigenvector which is derived from the original correlation or covariance matrix and the coefficients of the second principal component. And therefore, the last, that is the kth eigenvector, will be associated with its coefficients ak1, ak2 till akk, which indicates the kth principal component. So, every eigenvector is going to indicate a specific vector which highlights a variance along a specific dimension. Suppose you have the data distributed as shown in this diagram. Assume the new transformed axes are y1 and y2, where y1 and y2 are the first and the second principal components which is derived from the given data set. Now, you find the distribution of the data along the first principal component is more when compared with the distribution of the data along the second principal component. Now, this can be understood by the farthest data along the y1 axis and along the y2 axis. So, in the along the y1 axis, you can find the farthest data on the left hand side is this and the farthest data on the right hand side is this. Now, the distance between the two farthest data along the y1 is large when compared with the distance of the two farthest data along the y2 axis. Therefore, it can be said variance of data along y1, that is the first principal component, is very high when compared to the second principal component. Therefore, when you want to analyze your data, you can choose the component y1, the first principal component y1, for the purpose of understanding the data, and you can ignore the second principal component. So, originally we started with two axes x1 and x2. After computing the principal components, you end up with two principal components. Among these two principal components, one principal component may be effectively used for the purpose of visualizing or interpreting our data. This diagram clearly shows the variance or the distribution of the data along the first principal component and along the second principal component. You can find the variance along the first principal component is very large when compared with the variance along the second principal component. Now, till this what we have understood is principal component actually rotates the multivariate data set into a new configuration, and this new configuration will be very easier to interpret the data set. Now, this principal component analysis, its purpose is to simplify the analysis of the data and hence to simplify the data visualization. It actually takes a look into the various relationships between the variables and hence it will look in for patterns associated to various variables. So, ultimately we are trying to identify certain patterns. Here the patterns are the features are nothing but the dimensions available in the given data set. Now, let us understand the fundamentals behind principal component analysis. For calculating the principal components, we should know two fundamental things. One is the variance, another one is the covariance. Variance we have already discussed in one of the earlier module, one statistical metric or measure which actually indicates the spread of data. Now, given a data set, if I want to identify how the spread of data is, then you can make use of the measure called variance. The equation related to variance is similar to or identical to standard deviation equation. So, variance is equal to sum of the difference between the data and the mean square divided by n minus 1, where n is the number of elements in the data set. Now, this variance is actually calculated with respect to a single dimension. Suppose if you calculate the same with respect to two or more dimensions, then it is called as covariance. So, as the name indicates, co means between two dimensions or two or more dimensions. So, the same variance equation if modeled with two variables x and y, then you will get two means x bar and y bar. So, the difference between the data points along the x axis and the difference between the data points along the y axis will be considered. So, xi minus x bar multiplied by yi minus y bar, the whole divided by n minus 1. So, before computing the principal component analysis, we will have to calculate the covariances between various dimensions. Covariance actually can be derived from two entities. One is the covariance matrix, another one is the correlation matrix. In covariance matrix, the variables must be associated to same units and the emphasis on the variables will be associated with the most variance. So, any variable which highlights higher variation will be considered for the purpose of calculating the variance. Correlation matrix is actually a standardized form of the covariance matrix. In other words, the variables are standardized, that is they will be in the range of 0 to 1. Now, the variables over here can be having different units which is not same as the covariance matrix, and all variables have same impact on the analysis. In other words, every variable is given an equal chance for analysis. The mean eigenvalue in covariance matrix is not equal to 1, but the mean eigenvalue in correlation matrix is equal to 1 since the variables are normalized. So, you can make use of either a covariance matrix or a correlation matrix for the purpose of computing the eigenvalues and hence the principal components. Now, let us take a two-dimensional data set and then understand how covariance calculation happens. Here in this data set, you have two variables, one is hours, another one is mark. The hours indicates the time spent by students and mark indicates the various marks scored by the students, and we are now trying to identify is there any relation between the variable called hours and mark. So, what we can do is you can make use of the covariance equation for the purpose of calculating any relation between hours spent by student and the marks scored by the student. Now, let us take the two variables h and m. Now, for the variable h you can calculate an average and for the variable m you have another average. Now, take the differences between the values of h and its average. Similarly, identify the difference of the values of m and its average, so which is indicated here. Then multiply these differences, sum them. Now, based on the sum, you can easily make use of the equation called the covariance equation, which is already discussed. So, here x will be treated as the hours spent and y will be treated as the marks scored by the students and n will be the total number of elements in the data set. Now, with this information you can calculate what is the covariance between the hours spent and marks scored by students. Having understood what is variance, what is covariance, and how a simple covariance can be calculated. Now, let us jump to principal component analysis and the steps involved in calculating the principal component analysis. Now, consider a data with n dimensions. The first step is you will have to calculate the correlation matrix. The correlation matrix can be calculated first by means of subtracting the data by its mean. Then you will have to calculate the covariance matrix. From the covariance matrix, calculate the eigenvalues, eigenvectors of the covariance matrix. Once the eigenvalue and eigenvectors are calculated, then you are going to reduce the number of dimensions. Now, how the dimensions may be reduced is based on the eigenvalues. The eigenvalues are sorted in descending order, and based on the values and the importance of the value, the corresponding dimensions may be chosen. So, now with the help of new chosen eigenvalues and their corresponding dimensions, you can analyze the data with the selected dimensions alone, where the number of dimensions chosen will be very less when compared with the actual number of dimensions available in the data set. Now, how to derive the new data is, that is, originally you may have a data, now you are going to transform that to a new dimension, new set of dimension. How this transformation happens is, you will have to take the row feature vector. The row feature vector in your matrix is nothing but the rows indicating the eigenvectors with the row 0 mean data. The row 0 mean data is the mean adjusted data and the transpose of that particular matrix. So, if you compute the product between the row feature vector and the row 0 mean data, then you will get the new data. Now, if this new data is plotted with respect to the selected dimensions, you may end up with completely different visualization of your original data, and this visualization will help you in understanding the data in depth. Now, let us take an example. Consider a data having two variables x and y. X has some set of values, y has some set of values, the total number of values is 12. Now, if you plot the given data with respect to the two variables x and y, the plot will look like this. Now, using this plot, if you want to understand whether along the x axis or along the y axis the data shows variation, means if you take an intersection of this two dimensional plot, you will find both along the x axis and along the y axis there is equal variation in the data. So, the spread of data is going to be approximately same along both the dimensions. Therefore, what is that you need to do is, to get a better understanding of this data set, you need to transform the existing dimensions to new dimensions using principal component analysis. So, the second step is subtract these data with its mean. So, you will have to calculate the average of x, average of y, and then subtract this average with respect to every value of x and every value of y. So, the mean adjusted data will now look like this. So, the average for the x is approximately 1.8 and the average for y is approximately 1.9. So, if you subtract 1.8 minus 2.5, you get around 0.69, that is 7. Similarly, if you subtract 1.9 with respect to 2.4, it is 0.49. So, this mean adjusted data is what you are going to make use of for computing the eigenvalues and eigenvector. Now, with the computed mean adjusted data, you will have to calculate the covariance. So, covariance can be calculated using the equation which we discussed earlier. From the covariance matrix, you will have to calculate the eigenvalues and the corresponding eigenvectors. Now, with the help of new eigenvalues and eigenvectors, you can come up with a completely new plot. Now, the zero adjusted data which we have calculated as part of step 2, when plotted here, you can find the two eigenvectors, one represented by means of minus 0.73517 and 0.67787 will be one axis, and the other eigenvector minus 0.677 and minus 0.73517 will be the second eigenvector. The two principal components, these two eigenvectors now becomes the principal components for the given data set. In the earlier discussion, we understood the principal components are completely orthogonal. Orthogonal means they are perpendicular to each other. So, if you take and plot these eigenvectors, you will find these two new axes coming into picture. So, these two new accesses are calculated based on the two eigenvectors that we have derived. Now, if you take a look at this scatter plot, you will find the distribution of the mean adjusted data with respect to the two principal components. Now, among these two principal components, you find along one of the principal component, the variance or the spread of the data is high. Now, when you have two eigenvectors, now it is our decision to decide whether to take both the eigenvectors or only one eigenvector for our analysis. Our objective is to reduce the number of dimensions and thereby enable easy understanding of data. Therefore, in this example, we are going to leave one of the vector among these two, and you can choose one, say for example minus 0.677 and 0.7351, that is the vector represented by these two values for the purpose of analysis. Now, what does it indicate? This vector indicates a high variation in your data along a specific dimension, and that particular principal component may be chosen for analysis. Having derived the eigenvectors, that is the principal vector with which you are going to analyze the data, now you will have to derive the new data set. The new data set is derived using the equation rho feature vector multiplied by rho 0 mean adjusted data, and therefore, the new data will be this data. So, the transformed x and y data is indicated in this table. Now, if you plot this transformed data, this is the scatter plot which you are going to get. Now, let us understand how this new data may be used for the purpose of calculating the older data. The new data is calculated based on the equation rho feature vector multiplied by rho adjusted data. Now, if you want to calculate the rho data which is adjusted with respect to the mean, you will have to take the rho feature vector to the other side of the equation, which is nothing but inverse of rho feature vector. Inverse of rho feature vector is nothing but the transformation of the rho feature vector. So, the rho adjusted data now will be equal to the transformed rho feature vector multiplied by the final data. Now, if you add the original mean to this product, then you will regain the original data. So, you can understand whether the data which you have derived based on adjusting the mean and the new principal components are representing your original data by means of getting back to the old data using these derivations. Now, how to interpret the principal components? Let us consider a data set which is used for understanding whether a place will be suitable for residential purpose or not. So, this data set is almanac data, and this data set is used for rating places based on 9 criteria like the climate, terrain, housing, healthcare and environment, crime, transportation, education, arts, recreation and economics. These are the 9 parameters with which you can rate a particular place. Let us assume C1 till C9 be the IDs given to this data set. First thing is, you will have to examine the eigenvalues to determine how many principal components should be considered. So, the eigenvalues for each and every one of the attributes are displayed here. Now, you should understand among these 9 attributes, which are those attributes that are very much essential for analyzing the data. Now, you can first analyze what is the proportion of an eigenvalue with respect to all these components. Now, sum all the eigenvalues, which is 0.5225, divide every eigenvalue with respect to the sum. So, 0.3775 divided by 0.225 is equal to 0.722, in other words 72%. Similarly, do for the rest of the thing. From this proportion, you can understand the first eigenvalue itself contributes to 72% of the variation in the given data, and cumulatively when you take a look at it, you can find the first 3 eigenvalues alone contributing to almost 87% of the variation. Now, how to interpret this is, as I already mentioned, you take the eigenvalues, you sum all these eigenvalues and divide each and every eigenvalue by means of the respective sum. So, when you divide it, you will get a percentage value which indicates to what extent, that is to what percentage extent it shows a variance with respect to the given data set. Secondly, you need to compute the principal component scores. Now, for computing the principal component score, once you run say any algorithm that may calculate the principal components, you can now identify the first principal component y1, indicating to what extent the 9 attributes that we discussed earlier may contribute towards the understanding of the data set. So, here the 0.0351 indicates climate attribute contributes to say 0.0351 times of understanding the original data set. Similarly, the housing parameter contributes 0.0933 times for understanding the original data set. So, now this is nothing but a principal vector, principal component vector, or it can be treated as the first principal component for modeling and understanding our data set. Next, to interpret the component, that is each of the component, you need to compute the correlation between the original data and the variable based on the principal components. Now, when you take a look at the 3 principal components, here in this example, first 3 principal components were taken and they were used for understanding how these variables may affect the original data. Along the first principal component, you can find few of the data like housing, health, transportation, arts and recreation by means of their higher value. So, 0.54, 0.78, 0.5, 0.9, 0.5, these are the attributes that have higher value. Now, it means these 5 values together can help in understanding whether a place can be rated first or not. Along the second component, you can understand say a larger negative value minus 0.605. A larger negative value here indicates that health, if it is going to be a negative value, then it indicates that place may not be suitable for say residence purpose. And along the third component, you can find crime and recreation are having higher value, which means a place that has more crime also contributes for more recreation in that particular environment. So, now you can understand from the first principal component, when you want to rate a particular place, the 5 attributes like housing, health, transportation, arts and recreation are highly valuable for the purpose of understanding and rating the given place. Therefore, among these 9 attributes, now if you can depend on these 5 attributes, you may be in a better position to clearly say whether that place will be suitable for resident purpose or not. So, to summarize, we discussed about the various steps involved in principal component analysis, which is an important dimensionality reduction technique. This dimensionality reduction technique works on very large data set with very high dimensions participating in it. One important benefit of principal component analysis is you can examine the variance associated with the principal components, and accordingly certain principal components may be chosen for transforming our data to new dimensions and hence interpret the data and analyze the data in a better way. It is used for identifying key dimensions that may be useful for analysis. Thank you.